gentlemen, class recording has started. Hopefully the wind will make it listenable. So. Okay, today we continue on with our discussion of applying Newton's second law to different situations, and we talk about friction today. In the outline that I've given you, there are several pictures. Those pictures are going to show up on the board today, but there's going to be a lot of sort of commentary that goes along with it, which means you might not have to write down everything that shows up on the board. And there isn't a place to write down everything that shows up on the board. So you have to kind of make sure you get the information, write down either as little or as much as you want. So with that being said, before we talk specifically about friction, let's talk about net force. First, net force. We talked about two ways that we can represent net force. How do we represent net force? Okay, so we can just go F net, right? Or we can do the little sideways sigma, right? Or we can do sigma F. Those are both ways that we use to represent net force. But more importantly than actually representing net force is more of the what does it mean. So what does the net force tell us? It's the sum of all forces, or the combined effect of more than one force that is acting on an object. So the combined effect of more than one force acting on an object, or the sum of all forces acting on an object. So mathematically, we're adding all the forces up. Sometimes that might mean we subtract. If we have a force that's in the opposite direction, it's negative, blah, 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 blah. Okay? But when we talked about Newton's first law and Newton's second law, we talked about the idea that an object is only going to change what it's doing or accelerate if the net force is not equal to 0. So the motion of an object is only going to change if the net force is not equal to 0. All right, we're good with that? Those are old concepts. Next, let's talk about new concept, friction. Friction, by definition, is a contact force that opposes the motion of an object, or it can oppose some applied force if the object doesn't move, which we're going to talk about in just a second. The most important thing you have to remember about friction is that it is an opposing force. It has to go against something. It has to go against something. And we'll look at some instances later on today where it opposes certain stuff and where it opposes other things. And we'll keep coming back to that idea as we go along. So a contact force that opposes the motion of an object, or an applied force if there is no motion. All right. We okay so far? Okay. Let's talk about this picture right here, which you have a copy of in your outline. So this fella, he decides he's got to get himself in better shape. So what better way to do that than to buy yourself a flexerciser?
He's wearing jeans.
Yeah, he's wearing jeans. So,
And a polo.
I mean, that means in a couple months he's probably going to be wearing jorts too. So, all right. So this guy, he gets his flexerciser, and the delivery company apparently did not inform him that their version of delivery was just to drop it into his driveway. Didn't bring it in the house or anything. And apparently he doesn't have like a cart or a wagon or a dolly or anything to put it on wheels. So the best thing he could think of is to lasso it and just drag it into the house, like he was roping cattle or something, okay? So, he's got his flexorciser in his driveway. He's got his lasso. He lassos his flexorciser. And then he applies a force. Pulls on the flexorciser like such. Okay? You can use colored pencils here if you would like it. But something unfortunate happens. He pulls on the flexorciser and it doesn't go anywhere. Okay? So, if this object is not moving, what has to be true? Look. There has to be the same amount of force on the other side, which would make the net force what, Lily? 0, right? So there has to be another force in this direction. And like Lily said, how big does that force have to be? Exactly the same as what he applied to the flexorciser. Now, does it matter where it comes from? No. It could be somebody with another rope, another lasso over here applying a force in this direction, right? Could be somebody doing that. That happens sometimes. If you think about back when we did the skateboarding lab, at the beginning I pulled on the cart. At the beginning I pulled on the cart, but remember somebody was holding the other side of the cart and it didn't go anywhere. Because they were pulling just as hard as I was pulling, but in the other direction. But in this case, in this picture, is anybody pulling in the other direction? No. Doesn't really look like it, right? But if that object doesn't move, there has to be another force. So, just to review, this is exactly what we talked about. Okay? Man applies a force to the box, but it doesn't go anywhere. Why? Because the net force on that box has to be equal to 0. If there's no motion, there has to be no net force. Net force equal to 0. And if the net force is equal to 0, there has to be another force on that box. How big does it have to be? Exactly the same as whatever this guy's pulling, so that it balances out and the net force ends up being 0. Okay? Say again? No movement. No net force. Okay? And that means that if the net force is 0, that means if the net force is equal to 0, there has to be another force on it. It has to be exactly the same size, but in a different direction. Good for him. Yeah. That just depends on which way it's going far, right? So that's, we can sort of mess around with the positive and negative, but regardless in this case of whether we call towards the right positive, or if we go this way, regardless of whether we call towards the right positive and towards the left negative, or whether we call towards the left positive and towards the right negative, it would add up to 0 because one's going to be positive, one's going to be negative. Okay? So that's really up to us to decide before we go on. Okay? All right. But in this case, right, of this guy pulling this box, there isn't another person pulling on the other side, but there is what we call static friction. Static means what? We say something is static, that means what? It stays the same, it doesn't change, it stays still, whatever. Okay? Static friction is a frictional force that prevents an object from moving when a force is applied to it. So static friction always opposes some applied force. If we go back to this picture. That purple force is opposing the red. The purple force is opposing the guy pulling. Let's say this guy gets tired and he stops pulling. Does the frictional force stay there?
Yes. No. Wait. It's not
If the frictional force stayed even after he stopped pulling, what would this box start doing? Start going towards the left in this picture. And that doesn't happen. Remember, frictional forces always have to oppose something. In this case, they are opposing this applied force. Okay? Now, so this guy pulls on the flexorciser and nothing happens. What do you think he probably does next? He pulls harder. But guess what? Nothing still happens. So he pulls harder and nothing still happens. What had to have happened to the purple force?
It increased.
It had to have increased as well. How much did it increase? Just as much as the red one. Why? Because this guy pulls harder and nothing happens. Static friction is not a constant force. SF, the force of static friction, changes with an applied force to keep the net force equal to 0. So static friction is not a constant force. It can change depending on how hard we apply a force to an object. Does that happen indefinitely?
No.
It can't. Why not?
Because then nothing would move.
Nothing would ever move, right? If static friction always opposed any force that we applied to an object, we would never get anywhere, right? The forces would always balance and the net force would always be 0. So, this graph illustrates how static friction works. First, let's make sure we know what we're looking at here. X-axis, applied force. That's how hard you're pulling. Y-axis, frictional force. That's what friction is acting on an object. Here, the static region. We see here through the static region that that line goes straight up. If we were to look at the ordered pairs, the x-coordinate, y-coordinate that goes along with this, what would we see about that whole line?
It would be equal to 0.
Well, how would the coordinates match? Y equals x, right? If we apply a little bit more force, friction gets a little bigger. What's the slope of this line? 1 over 1, right? Because they have to be equal. But we see here that there eventually comes a peak, right? And that peak is labeled as Fs max, the maximum static friction value. Why would the maximum static friction value be important?
That's when. That's like more.
You have to apply more force than that in order to create what?
Movement.
Or, well, before we create movement, we have to create a acceleration gets caused by what? By net force, right? If we apply a force greater than the maximum static friction, are these two forces balanced anymore? No, they're not. Now, red is bigger than purple. And if red is bigger than purple, what's going to start happening?
It's going to start moving.
It's going to start accelerating. Right? Does that make sense? So, this guy can't move his flexorciser. So he brings in this hoss. Right? How do I know this guy's a hoss? He wears a hard hat. It's a dead giveaway. Yeah, like a hoss.
What's a hoss?
Come on.
Never heard that. It sounds like a brand of shoes.
Yeah, it would be like a brand of shoes that like guys who like dig ditches and work on buildings wear, because they're hosses. So, I mean, see, look at this guy. Look at how much force he can apply. 4 lines worth of back force. Whoa. That's just not that's not normal. All right. So this hoss comes in. Okay. He's got his hard hat on. He's got his back brace on. Okay. That's always a dead giveaway too. If you just wear a back brace around because you know you're gonna have to push heavy things, you know, it's just right. So this guy applies a huge force. If you don't understand what a hoss is, just call him Guy. All right. This guy. Okay.
No, I got it.
Okay. So this guy applies a big force and this box starts to move. Why? Because now there is a net force acting on that box. And if there is a net force acting on that box, it starts accelerating. Because static friction can only increase to a certain level. The force that the guy is applying is greater than the maximum static friction. So we create an unbalanced force, and that causes a change in the motion. So the maximum static friction is important because we have to apply a force greater than that value in order to create an unbalanced force or a net force in one direction, and that causes acceleration. Say again?
Is he wearing jeans too?
Oh yeah. And probably steel-toed shoes as well. So that's a Haas requirement. Steel-toed shoes. So he's probably got some tattoos under here as well. So what? I just said probably. Said probably. You know. That's true. But the reason why stereotypes exist is because on a lot of levels they're true. Not all the time, no, but that's why they're stereotypes. So, right? That's why they're stereotypes, because, you know, on some levels they are true. Not always, and you shouldn't assume that just because somebody is a certain group, they're stereotyped in that way.
Yeah,
But
like how teachers give homework credit and extra credit. You
Yeah.
can't stereotype me.
you can't. Don't push me into that box, all right? Don't. That's right. I'm outside the box. So, all right. Are we good with maximum static friction? Okay. So, but if we take a look at this graph again, once we hit that maximum static friction value, what do we see happens to the friction value on this graph? It goes down and it also stays what?
Constant.
Constant. Okay? So, is it harder to get something to start moving or to keep it moving once it's already going?
Start.
It's already harder to get something to start moving. Have you ever tried to move some furniture around your living room? Right?
Just a little jut,
Right?
and then you get
At the beginning, it's kind of hard to get that couch to start moving. But once it's already moving, it's easier to keep going, right? Because once we pass that maximum static friction value, the friction switches between static friction and now it becomes what we call kinetic friction. So kinetic friction, kinetic is a word we've heard before, right? Kinetic means what? Movement, right? So kinetic friction, or sometimes we call it sliding friction, is a frictional force that acts on a moving object in order to slow it down. This is generally what you guys think of as friction. For example, I take this book, right, and I do this with it. Okay? What eventually happens to that book? It stops. Why? Because of friction, right? What friction? Oh, leave it there. Demonstration's not over yet. So, friction acts which way on things? Opposite or negative, right? So whereas static friction opposes a force, opposes you pulling on an object, kinetic friction opposes motion. It goes against the way that it's moving. Alright? So, kinetic friction is always less than the maximum static friction for a given object. That doesn't mean that all kinetic frictions are less than all maximum static frictions. That's not what it means. But if we're talking about the same object, it has a greater maximum static friction than kinetic friction, meaning that it's easier to get something to keep going than it is to start it moving in the first place. Good for it.
On the graph, how it's after the friction decreasing
Yep.
at the same constant.
Yes.
And then
The amount of kinetic friction stays constant as long as that object is moving. And that's going to be an important part of this next part, okay? So, in the next picture, so this Haas, he did his job. He got the box to start moving, so he just shoves it across the floor, right? And much like the book that we saw sliding across the floor here, eventually what's going to happen to that box? It's going to stop. Are the forces on it balanced as it slides across the floor? No, because what is it doing as it slides across the floor? It is slowing down, which is a form of acceleration, right? Slowing down is acceleration. So there has to be a net force that is not equal to 0. Kinetic friction acts on objects as they move. Okay.
Can you go back one?
Yeah, good.
Thank you, sorry.
Oh, should probably put the rest of the words up there. All right, we good with this? So let's take a look at this picture. All right, so if we are to look at the forces on this box as it slides across the floor, there'd be this force here, right? And then there would be this force here. What do we know about green and blue? They have to be the same, right? Because is the box moving up or down? No. But if it's moving to the right, but it's slowing down, there has to be this force, right? That force there, that is our FKF, the force of kinetic friction. That force of kinetic friction will continue on that box until it stops. Always in the opposite direction, causing it to slow down. Good there? All right. Once it stops, what happens to kinetic friction? It stops. Farr says it goes away. Keenan says it stops. Okay? Because we said friction always has to oppose something. If that frictional force, and Joe, this is why I didn't want you to move it, right? If that frictional force continued to act on that book even after it stopped, what would it start doing? It would start going back the way it came from, but that doesn't happen. Remember, friction has to oppose something. So, once the box stops moving, does the kinetic friction force still exist? No. If it did, that box would start moving back in the direction in which it was previously moving, or back the way it came. Kinetic friction only opposes motion. No motion, no kinetic friction. All right, we good there?
No.
Yes, ma'am. Say again. Sine friction. friction, kinetic friction acts on objects that are moving. All right, everybody. I know it's been hot. I know it's a hot day. It's kind of uncomfortable in here, but you deserve this next one, right? Are you ready, everybody? Oh, well done. Okay. So, hold on. Wait, whoa. You're done with the slideshow. You're not done with class just yet. Right. So, you know that packet that I told you?
Yeah.
That's what it means. That's objects that are moving.
Oh.
This packet that contains these concept development pages. So, concept development practice page 5-1 deals with this idea of friction, static friction, kinetic friction, etc., etc., etc. I asked you last night to take a look at it, see if you could do it, okay? So what I'll do is here, you have about 10 minutes left of class. I will put the answers up on the board, so if you did it, you can check it. If you didn't do it last night, it might be a good idea here to talk about it. If you aren't sure about something, you can check with me on it and see how it goes, right? Tomorrow, we can start in on impulse and momentum. Good stuff, everybody, good stuff. So, you'll sleep good tonight. Rest up.
Is it hard?
No, it's not hard. It's just, it's a lot of good practical application. It really is. Like, it's things that you're going to be like, oh, yeah, like that's why we do it. Impulse and momentum, which is where we're going tomorrow.
I still don't remember the last word.
All right, so those are the answers.